Let's review what we covered in these sections in chapters 2 and 3. Of course, you should go back to the original class notes and videos for more information, but here we'll just summarize the main ideas. And yeah, here in chapter 2 we're looking at some basic mathematical structures. So the first one we looked at sets, collections of objects like numbers, and yeah, there's lots of notation to get right. So in this example, S is the set of these four numbers. So you write the elements between braces with commas between each of the elements. More notation. Yeah, this symbol is an element of. So for example, 10 is an element of this set S. This notation is a subset of. So it allows equality. This one doesn't allow equality, so this means a proper subset. And here we have the empty set. Okay, so the symbol means the set with no elements. More notation. So the set of all subsets, that's called the power set. P of S, that's the power set of S. For example, the power set of this set, okay, so the set just containing the numbers 1 and 2, its power set. Well, what are all the subsets of this? Well, you have the set itself, you have the empty set, and in between those two you have the set just containing 1. Okay, so this is a subset of the original, and the set just containing 2, that's also a subset. Alright, so power sets. This notation means cardinality, so the number of elements of a set. So the set S has cardinality 4. And also this power set also has 4 elements. So its cardinality is also 4. Yeah, you have to be a little bit careful. Alright, so you can see this the stuff inside these elements. So this element is a set itself. Well, so are these. But when you're counting elements, it's just four elements here. And the cardinality of a power set is always a power of 2. So we saw why that was true. And one more thing in this section, the idea of a Cartesian product. So if you take two sets A and B and look at all possible ordered pairs, something from the first set comma something from the second set. Then that set of ordered pairs, that's called a Cartesian product. And we're showing it here in set builder notation. So the set of all ordered pairs such that little a comes from the first set A, little b comes from the second set B. Yeah, we haven't used Cartesian products much in this course, but it's another way to think about functions. So functions are ordered pairs with an x and a y. Okay, next we looked at set operations. So other ways to combine two sets to make a new set. You can have a union with this notation, intersection, set difference, and a plus with a circle, that's symmetric difference. Okay, so I can ask you to work out these for different sets. In this example, A is the set containing 1, 2, and 3. B contains 3 and 4. Well, the union just means everything together. 1, 2, 3, and 4. Of course, you don't write 3 twice. For a set, you just write things once. The set difference, B minus A, so that's everything in B, but take away anything that also is contained in A. Okay, so we're looking at B, anything in B also in A. Yeah, this 3 is also in A, so we're going to take that away. But 4 is in B and not in A, so the set difference B minus A is 4. For the symmetric difference, it's the same as the union, except you take away what's in the intersection, what's in the overlap. Yeah, so A intersection B is 3. And if you take the 3 away from the union, you're left with 1, 2, 4. Okay, so the symmetric difference, it's just this stuff on the side, so it's the union minus the intersection. Okay, how about if we have the intersection of 3 sets? So A intersection B intersection C. Yeah, so the intersection is associative, so it doesn't matter how you do the intersection. You could do B intersection C first, then A intersection that. But since we've already worked out A intersection B, we can do that first. So that's 3. And C is 1, 4. This new set, so what's the overlap between these two? Well, that's the empty set. Alright, so the intersection of these 3 sets is empty, so there's no elements that are common to all 3. Okay, next idea, very important, the idea of a function. So a function, it's a mapping from one set to another. Here's the definition. So a function f from set A to set B sends every element of A to a unique element of B. And we write that like this. So f colon A with an arrow to B, that means f is a function from A to B. A is called a domain, B is called a codomain. And yeah, note these two key words. So to be a function, everything in A has to go to a unique element of B. Example 3, let A be this set, let B be this set. Let's set up a function, or, well, maybe a function. So this f sends 2 to 4 and 4 to 5. Okay, so it's sending things in A, 2 and 4, to things in B, 4 and 5. A different mapping here, this G sends 2 to 5, 4 to 5, 6 to 4, and 4 to 4. Then the question, are f and g functions from A to B? So, yeah, for these very simple functions, it's a good idea to draw the picture. So use arrows to show what the function is doing. Okay, so this f, it's from A to B, so we have 2, 4, and 6, and arrows from those to B, 4, and 5. Okay, so for the picture, f of 2 equals 4, so 2 heads to 4. F of 4 equals 5, so we have this arrow. So is that a function? Well, no. So yeah, there's a problem here. So to be a function, everything in A has to get sent somewhere. But 6 doesn't get sent anywhere, so f is not a function from A to B. Okay, how about g? Is g a function? Okay, so g sends 2 to 5, 4 to 5, 6 to 4, and 4 to 4. Well, yeah, you can see, well, okay, G is sending everything in A somewhere, so we don't have this problem, but we have a new problem. 4 is getting sent in 2 different directions. Okay, so 4 is not getting sent to a unique element in B, so that means that G is not a function either, for a different reason. All right, so again, to be a function, you have to send every element of A to a unique element of B. Okay, how about this? This h is given by h of 4 equals 6, h of 5 equals 2. To show that this is a function from B to A this time. Yeah, so this h is sending elements of B to elements of A. And yeah, so everything in B gets sent somewhere. H of 4 equals 6, h of 5 equals 2, and 4 is getting sent to a unique place, 5 is getting sent to a unique place. So this h is a function. It sends every element of B to a unique element of A. Yeah, what about this 4? Does that cause a problem? No, that's fine. As long as there's nothing missing over in the domain, then it's a good function. Okay, the range of h, yeah, so those are the elements in the codomain that get hit by something coming from the domain. Okay, so 2 is in the range, and 6 is in the range, but 4 is not in the range. So the range of h is just 2, 6. And the fact that that is not equal to the codomain A means that h is not onto. Okay, so any missing numbers like this in the codomain means the function is not onto. Okay, so being onto, that's the main property of a function. The other one is being one-to-one. Okay, so one-to-one means that, so a function's one-to-one if two different elements in the domain always get sent to different elements in the codomain. So this function is one-to-one because 4 and 5 get sent to different places. If 4 went to 6 and 5 went to 6, then this function would not be one-to-one. All right, so this h, it is a function. It is one-to-one, but it's not onto. But if you do have a function f from A to B that is both onto and one-to-one, then it's called a one-to-one correspondence. Yeah, I noticed people getting a bit confused by this in the homeworks. So to be a one-to-one correspondence, you also have to be onto. Maybe a better name is the other name, bijection. Okay, so if you do have a bijection, if you have a one-to-one correspondence, so that's the case that you can reverse all the arrows and get a new function. And that function is called the inverse with notation. It looks like a power, but it means the inverse. For example, we have a g from the real numbers to the real numbers given by g of x equals 2x plus 5. So yeah, it turns out this is a one-to-one correspondence. Find g of negative 1 and g inverse of 1. Alright, so yeah, so we saw examples how to prove that a function like this is one-to-one and onto. So we're just assuming that here. Okay, so what is g of negative 1? Okay, so if you put in, give g the input negative 1, it just means you're substituting negative 1 for x. So it's 2 times negative 1 plus 5. That's negative 2 plus 5, 3. So if negative 1 goes into g, then 3 comes out. For an arrow picture, yeah, we have an arrow from negative 1 in the domain to 3 in the range. Okay, so that was easy, but how about the inverse? Okay, so what's g inverse of 1? Well, we don't know what the number is, let's call it x. So if g inverse of 1 equals x, okay, remember the inverse reverses the arrow, so if g inverse of 1 is x, that means that g of x equals 1. Well, what x satisfies this equation? Okay, so if g of x equals 1, that means 2x plus 5 equals 1. Alright, so we're solving a linear equation. So x has to be negative 2. Alright, so that's the number we were looking for. So g inverse of 1 is equal to negative 2. And yeah, you can double check that. So g inverse sends 1 to negative 2. That's the same as saying g sends negative 2 to 1. And yeah, if you work out g of negative 2, that is 1. Alright, so yeah, these inverses, yeah, nothing to do with reciprocals. It's you're reversing the arrows for the function. And yeah, one last function topic, composition of functions. Okay, so that just means you're putting one function inside another. So if you take, say, a number, or take an input x, work out g of x, and then work out f of that, then that's called a composition. And it has this notation with a little O symbol. And the way to read this is f after g. Okay, so you hit this input with a g first, then with the f. And this is the composition of g and f. Okay, so you're getting a new function. So this is a way to combine two functions. All right, so yes, take a look in the notes for that section. But let's get on to the last topic. In chapter 2, we looked at matrices. Okay, so a matrix, they can be different sizes, but they're just rectangles with rows and columns of numbers. This matrix has 2 rows and 3 columns, so it's called a 2 by 3 matrix. But they could be any size. You could have a 1 by 1 matrix, so just with one number. But if you have 2 matrices of the same size, then you can add and subtract them just by adding and subtracting the corresponding entries. And yeah, these numbers are called the entries of the matrix. But if you want to multiply 2 matrices, then that's a bit more complicated. So you're really multiplying rows of the first matrix by columns of the second matrix. Okay, so with that same m, but changing the n, or yeah, here's n. Also, n is a 3 by 2 matrix. So we can multiply these together. Okay, so it's this row by this column first. Okay, so you multiply the corresponding entries and add them all together. So we do that here. Okay, so it's 1 times 0 plus 2 times -1 plus 3 times 4. And if I did that right, that's 10. Okay, so the first row times the first column gives the number in the first row and first column of the answer. Okay, then so do the same thing. So the second row times the first column, that's worked out here. That gives 19. And then the same thing, multiply those rows by the second column to get these two and these two numbers. Okay, yeah, so it's a bit complicated. And yeah, for this to make sense, so we need the number of columns in the first matrix to match the number of rows in the second matrix. So those numbers were 3. Okay, so you can multiply 2 matrices if these two numbers match. And then the answer is going to be a 2 by 2 matrix. Okay, and a very similar idea is the Boolean product of 2 matrices. Okay, but we need 0, 1 matrices, so just containing the numbers 0 or 1, which we can treat like bits. 1 is true, 0 is false. And for trues and falses, zeros and ones, we can use the AND operation instead of multiplication, and the OR operation instead of addition. But doing it the same way, so multiplying rows by columns, that gives the Boolean product. And so you'd have Boolean product is written a circle with a dot. Yeah, more details in section 2.6. Okay, and just in chapter 3, we just looked at the first section on algorithms. So these are precise instructions to perform a computation or some task. And we wrote our algorithms in pseudocode. Just kind of a fake programming language just to get the ideas across. Okay, and in this section we just studied some simple algorithms. Max, so that finds the largest integer in a list. Okay, so the input is a list of integers, and then max just used a simple for loop to step through the list, and if it found a bigger number than the one it had stored, then it replaced the stored number with that bigger one, and just kept going until it got to the end of the list. Linear search, that also took a list of integers as input, but also another number that you're searching for. Okay, and then it stepped through the list until it found the given integer that you're searching for, or else if it got to the end of the list without finding it, it gave an output of 0, meaning not found. If the integer list is in order from smallest to biggest, then there's a much more efficient way to search. So that's the binary search. Just keeps breaking up the list into 2. We also looked at sorting algorithms, so putting lists in order from smallest to largest. 2 ways to do that. You have the bubble sort and the insertion sort, so 2 different methods. The bubble sort has the advantage of being very simple, at least, but not very efficient. So insertion sort, slightly more efficient, but more complicated. And lastly, an example of a greedy algorithm. So making change, starting with the largest value coins. All right, so these algorithms were all given in pseudocode, and a typical kind of question is to, I'll give you a specific input, and then you just describe how the algorithm works, how it produces its output. All right, so go back, take a look in that section 3.1. Make sure you're familiar with these algorithms. All right, so that was just a quick summary of what we covered in chapters 2 and 3.